Hello, am I audible?
Yes, sir. Good
Okay,
evening, sir.
great. Good evening. So today will be a revision session for quiz 2. So I hope everyone knows the syllabus, right? Uh, Mostly week 5 to 8, but you can expect one or two questions from previous week as well. So it's mostly week 5 to 8 only. Okay. So let me share my screen. Okay, how many of you have attempted the mock test for quiz 2? Just raise your hand. Okay, one, two, three, four. Okay, fine. So we'll be discussing few questions from that, and we'll revise the concept from week 5 onwards. Okay, so we have the syllabus from week 5 to 8, right? So mostly week for you, right? So if we talk about the week 5 concept, so what we have I discussed there. The first one is we start with the functional dependency part, right? So first we'll discuss about what is functional dependency. Then we'll discuss about how to find out the closure of an attribute. So everyone must know how to find out the closure of an attribute, right? Then how to find out candidate key, super key, number of super key, all those things, right? Then we should find out, we should check a decomposition part. Then we have dependency preserving part, right? Dependency preserving, right? So this we have in week 5. In week 6 is basically a normalization part. So we'll discuss all those things in detail in today's session. So first thing is basically a functional dependency. So when I say A determine B, okay. So when I say A determine B, what does this mean? Yes, anyone?
So this means A uniquely determines B.
Yeah. So A uniquely determines B. It means what? If A1 is determining B1, in that entire table, A1 should give me B1 only. If A1 is giving me B2, then we cannot, let's say that A determines B, right? So every unique value of A1 should give me uh, unique value of B1, like that, okay? So A1 uniquely determines B1 like that, right? This is about the functional dependency part. Okay. So the solution already given in this particular question, but anyway, we can discuss the concept of functional dependency here. So you can see this, we have this 5 columns we have, right? V, W, X, Y, Z, like that, right? Now, suppose I want to check V determine W, X. Now, is this functional dependency valid here? If not
Y-
valid, then
Yes.
what is how it is violating? So first check for unique values of B. So B is determining what? 9, 8. So B should determine 9, 8. B should determine 9, 8. Right? This is fine, right? If B is determining 9, 8, in the entire table, B is determining 9, 8 only. And here 9 is determining what? B 8, but we don't have any other different pair of 9 in the same table. So you can see for all the 4 rows, this particular case is getting satisfied. So we can say we determine WX is applicable here. Similarly, what about YZ determining X? Is this holding or not? Yes.
No.
So check for combination. Y Z, like 7 5 determining 8, okay. 7 1 determining 8, okay. 2 2 determining 8, that is fine. 3 6 determining 8, that is also fine. So every value is unique here. So every left hand side value is unique here. So that's it, right? Anyway, it is going to determine the unique value, right? So right hand side is duplicate, that is fine. Okay, we are not dealing with the right hand side value.
Oh.
7 5 can determine 8 also, 7 1 can determine also 8. But 7 5 cannot determine any other value, right? Only 8, not 9, like that. So here we can say yz is determining x, but x is not determining yz, right? So this fd is not correct. Okay, so x determining yz, this reverse is not applicable here. This is fine. Okay, what about x determining yz? This is what we have discussed, right? So 8 also determining 7 5 and it also determining 7 1. This is not possible, right? So not correct. Similarly, y w determine z, right? Like that you can see here. So wy is what? W and y. So 9 7. So you need to consider the combination here, right? So 9 7 determining z, that is 5. So do we have 9 7? No. B 7 1. Do we have B 7? No. 9 2 2 9 3 3. So every left hand side value is unique. So anyway it will hold this particular functional dependency, right? So I hope this thing is clear. What is the concept of functional dependency? Any doubt in this particular concept?
Sir, how first we determines Wx is correct?
We determine x, wx.
Ah, yes, this one.
So B is determining 9 8. Here also be determining 9 8. Here also be determining 9 8, right? So
Oh, okay, okay.
here you can see it is satisfying the condition, right? And here 9 determining B, that is also fine because we don't have any other 9 again, right?
Okay, sir. Yes, thank you, sir.
So just understand if this particular example, simple one, roll number determines your name, right? So whenever I know the roll number, I can find out your name. But if I know the name, I cannot find out your roll number, right? Because there are multiple students with the same name, right? But roll number is unique in this case, right? So left hand side must be unique, right hand side can be duplicate, right? So roll number 21 F1 determining Raj, 21 F2 determining Ram, 21 FC determining again Raj. So that is fine because two students can have the same name. That is fine. So if I know the roll number, I can get the name. But reverse is not true. If I know the name, can I get the roll number? No, that is not correct, right? So left hand side value is unique, right? That is how the concept of functional dependency is there. And based on that, we generally design our database. Okay, so it should follow this particular functional dependency. I hope this thing is clear now about the concept of functional dependency, right? Now, how to find out the closure of an attribute, right? So, closure of an attribute. Let's take one example here. Yes, any question, anyone? You can simply unmute and ask if you have any question.
So that x2 yz is wrong because the x values are identical. Am I right?
X, Y, Z. Yeah. So if you
Yeah,
see
sir.
here, 8 is also determining 7 5 and 8 is also determining 7 1, right? That is not correct, right? So 8 should uniquely determine Y, Z. That is what we are saying. So left hand side
Okay, sir.
value uniquely determine right hand side value, but that is not the case here, right?
Okay, sir.
Yeah. Now, closure of attribute. Let's say we have a relation R having, let's say, A, B, C, D, E. We have 5 attributes, and let's say we have functional dependency like this. A determine B, B determine C, D determine EB, right? And let's say C determine D. Okay, so we have this four functional dependency. If I want to find out the closure of, let's say, for example, A, how to find out the closure of A? So first, whatever the attribute we are going to find out the closure, that will come here. So A will determine A itself, right? Now from A, whichever attribute we can determine, we need to add in that particular closure. So here from A, I can determine B. So I'm going to add B. Now from A or from B or from AB, can we determine any other attribute? Yes, anyone?
Yes, C.
C, C,
So C will be there.
C to D,
Again, C to D is there. So I can add D also. Now
and D to E.
D to EB, but B is already present, so we'll add E here, right? So this is how we can determine the closure of any attribute, right? For example, if I want to find out the closure of, let's say, for example, CD, right? In that case, how we are going to find out the closure of CD?
C to D, so if that is there, CD, and D to EB, so EB will be there,
Yes.
and B to,
To C.
Yeah.
Sorry,
Anyway,
okay, that is already there.
yeah.
So that's it.
Yeah.
that's it.
So you can see this is how we can find out the closure, right? So simple concept of closure, very very important. In every question, you need to find out the closure. So you should know how to find out, right? Simply first write down whatever is there for which you are finding out. For example, CD. Then from C or from D or from combination of CD, what we can add in that closure. So based on the functional dependency, we can decide that, right? So this is about the closure of an attribute. Any doubt in this particular concept?
No, sir.
Okay. Now, how to find out candidate key?
We can
It is a super
check,
key and
The
No, so
minimum
you
super
said we
key.
can
yes,
check the
minimum.
closure
Minimum
sheets.
check
minimum
the
super key.
Okay.
right hand side of all the functional dependencies in dependency set, and then we can check whether it determine all the attribute
Yeah.
in the
So
relation.
okay. So whenever we say candidate key, super key, or any key, so what is key here? If I take the closure of that key, it should give me all the attributes in that particular relation, right? All the attributes, right? All the
Yes.
attributes in relation R. So if I take the closure of any attribute or set of attribute, if they are giving me all the attributes present in the closure R of R, then we can say that particular combination or individual attribute is the key. So simply, if I take the closure of any key, that should give me all the attributes in R, right? But how to find out the key here? So the first thing is that suppose we have this relation R, right? So we have this 5 attribute. So what is the traditional way here? First, you can take the one attribute A, take the closure, see whether it is key or not. But in this case, if you observe, A is what? We are getting all the attributes here, right? We already find out the closure. That is
Hmm.
basically equals to R. So A is key here, candidate key here. We can say candidate key. But table can have multiple candidate key also, right? Then check for B. Is B candidate key here?
No.
No, it doesn't
Because from
define
B
any.
we'll get B, C,
A is
D,
not
E.
defined.
A will not be there, right? C is not candidate key here. D is not
No.
candidate key here, right? Now we know that from A we are going to get all the attribute, but from B, C, D, E we are not going to get any this R, right? Now we left with these 4 attributes. Now what you have to do? You need to take the combination of these 4 attributes. For example, B, C, then C, D, then C, E. Okay, then we left with B, D, then B, E. Any other combination? B, C, B, D, B, E, C, D. Okay, D is remaining.
D.
So check for all the combination in that case. Find out the closure of each of the case, right? That is the case you need to find out for every. This is how you proceed. Because if you consider candidate key A in that combination, so that will be a super key, right? So if you take any combination with A, for example, AB or AED, so that anyway you are going to get the R, relation R because A is the key here. Now this combination is basically what? It is a super key. So we can say combination of candidate key with any other attribute, with any other attribute is basically a super key, right? Or we can say candidate key is basically minimal super key. Attribute is super key here, right? And anyway, every candidate key is super key also. So every candidate key is super key also. Okay. So this is the long process that you need to do, right? But there is one trick. First, you can apply that, but yeah, and after that, you can check whether that is getting satisfied or not. So, what is that trick here we discuss? So, first, try to find out which attribute are not present on the right hand side of any functional dependency. Not present on the right hand side, right? So, B is present, C is present, EB is present, D is present. Only A is not present on the right hand side of any functional dependency. Then we can say A can be a part of candidate key. A itself a candidate key or it can be a part of candidate key. So first take the closure of those attributes which are not present on the right hand side of any functional dependency. See whether it is candidate key or not. If it is not, then take the combination of A with any other attribute like that. So in this way you need to proceed. Okay. So this is the process for finding out the candidate key. Anyone any doubt how to find out candidate key?
Sir, I have a doubt in the closure of CD.
Okay.
You have written in the functional dependencies D defines ZB. So does CD as a combination define E and B separately or EB together?
So CD will give me CDEB, right?
Yes, but D defines EB. But CD is a combination, isn't it?
Yeah. So from this, what we can say, CD also determine EB. Okay.
Yes, but not separately. CD doesn't define EB. CD does E. CD doesn't determine B. Separately or together it determines EB.
Yeah, separately determines EB. Yeah. Individual D determines EB, but we cannot say C determine EB. Right? This is not correct.
Yeah,
So
and
whenever,
no. Oh, okay, yes, yes. That's what.
yeah. So
Sir,
let's
I
say,
have a doubt.
yes.
Sir, if I add one more functional dependency in that example, like BC determines A, okay. So now BC is also a candidate key.
Yes. Yeah.
BC is also a but it is not a minimal, sir. So how?
How it is not minimal?
But there is
So
only one attribute there, no? A.
that is not a minimal thing. Whenever say we BC is a candidate key or super key, so we need to check whether individual B or individual C is a candidate key or not.
Okay.
Okay.
Subset of BC.
Yeah. Subset of BC is candidate key or not. Okay.
Okay. Okay. Thank
That
you,
we
sir.
have to.
Hmm.
Sir, after adding BC determines A, all the elements in R is in right side now in F. So now
Yeah.
what will be the candidate key?
Now in this case, first check for A, then check for B, C, D, E. Individual attribute you need to take the closure and see whether you are getting all the attributes or not. Then go with the combination, right? Like that B, C, B, D, B, E, like that. So what process we have discussed that we have to follow.
So
Okay.
we can have more than one candidate key inside the
Yes,
function.
yes. More than one candidate key is there. Yeah.
Okay, sir. Thank you.
So if you understand what we have discussed, let's try to apply that concept here. Okay. So question number 7 from mock test. We have this relation R, dependency is given. Which of the following is are the candidate key? So don't go with the option. We are going to find it out. So first tell me how to find out. Yes, anyone?
First, we mark out the right hand, the elements, sorry, the attribute from the right hand side and cut it out from the original relation like y, x, z, and v.
We. So we
So
left
So the
X, Y.
left
right.
out, yeah,
Yeah.
x,
After
y
this,
will be part of candidate key.
hmm. How to check?
Now we have to take check whether x, y can alone determine all the attribute. If they can, the cover
Hmm.
contains all the attribute. If they don't, we have to take combination with others, with other attribute.
Yeah. Okay. So what's the closure of X, Y here? Tell me. So X, Y will determine X, Y. Then after
X,
this,
Y, X to Z, Y and Y, Z to V and V to W. It determines all.
how?
X to, okay, no, W, Z.
It is
Yeah, so we
W
need
X
W.
and this is
W,
Y
X,
Z.
W,
Yeah.
X and W. Okay.
Combination is there, right?
So we need W also.
It is not determining all.
No, right?
We need W.
Then what you need to do? Take the combination of X, Y with remaining attributes. So X,
Hmm.
Y, V, X, Y,
W.
W, and X, Y, Z, right?
Yeah.
So find out the closure of X, Y, V.
X, Y, V, V to W, W to
Then
all.
W.
yeah,
All.
W, X, Z, right?
Hmm.
Z.
So we are getting all the attributes. So X, Y, V is a key. What about X, Y, W?
Again, it will get x w x to z, so x y z
Hmm.
and y z to
Z.
v and v
Yeah.
to w all.
Yes. What
Hmm.
about X, Y, Z?
Y z to v, v to w and w x to z. So again all.
Yeah, again all. So here three candidates key are there: X, Y, V, X, Y, W, X, Y, Z, right? So we have three candidate key, and if you see in the
Hmm.
option, we just have two. So there are two options correct here, right?
Hmm.
So but here we have three candidate key. So this is how we can find out the candidate key here. That's it. Okay. So anyone any doubt here? How to find out candidate key? This is clear.
Sir, so the thing you said about possible candidate keys, like um, if I have a candidate key, another candidate key will not have any intersection with that. Uh, is it like this? How to check minimal?
Sir, I have a doubt with XYW closure.
Okay, so see, first I will answer how to check for minimal. So if you see X, Y, V is a key, so we know that it is a key, right? Super key. But how to know that it is a standard key or not? So you need to check whether X or Y or V or combination of this is determining we are getting all the attributes or not. So
Okay.
subset is a candidate key or not, right?
Okay. And for different keys, we have to check separately. Like I have two keys, I have to check separately. Like uh, first key is minimal or not, or second key is minimal or not. Based on that, I can say
Yeah,
key
but
one and key
you
two
don't
are
need to do
candidate.
that, right? So first, anyway, we are finding out candidate key only, right? Not the super key.
Okay.
Yeah. So first find out candidate key, then any combination of CK will be a super key, right? So it CK is also super key itself. Yeah.
Hmm.
Okay. Yes. Second question.
Can
Closure.
you explain the closure of XYW?
Yeah. So first, what we are doing, XYW we determine XYW. So we are adding that in the closure. But if you see from WX, so we have W, we have X, right? From WX we can determine Z. So I'm going to add Z in the closure. And then from Y and Z I'm determining V. So I'm going to add V also in the closure, right?
Okay, yes.
Yeah. So you need to check the combination also like that. Okay. Okay. Great. So in some case, what may happen? In this case, XY is not determining all the attributes, right? Let's say, for example, in the closure of XY, you are getting XY Z, right? So here we are not getting all the things, right? All the attributes. Then you don't need to take the combination of XY with Z because anyway that will consist of this particular closure. Then take the combination of XY with those attributes who are not present inside the closure, right? So this is what we have to do. In some cases, suppose we have this R, let's say A, B, C, D, E, F, G, H. This is we have, and let's say we find out that on the right hand side of any function dependency, B, E, F is not present. So if you take the closure of B, E, F, suppose you are not getting all the attributes, right, in the relation R. You don't need to take the combination of B, E, F with A, then D, then F, then G, H. No, not like that. First, find out the closure of BEF. Let's say, for example, we have this GH only. So this is what we got from the closure. So you don't need to take the combination of BEF with G and H because anyway, it will give that particular closure itself, right? So what you need to do, take the closure, take the combination of those attributes which are not present inside the BEF closure or those closure, right? So in that case, you need to take with BEF A, then BEF C. That's it, right? D, okay, BEF C D as well because EFGH is present inside this particular closure. So in some cases, if you find out like that, you don't need to take all the combination, right? Just go for those combinations which are not present on the closure in the closure, right? Because anyway we cannot determine those. That's why we're taking the combination of that. Okay. I hope this thing is clear, right? What I said now.
Yes, sir.
Yeah. So you don't need to take the
Sir,
combination of
but
any
it
closure.
has B also, no?
Where?
In the right hand side, we are not supposed to take B also, no?
No. What I said first, after applying that condition that right hand side don't have this much attribute, right? So if you're taking the closure of this one and we are not getting R, suppose we are getting this one, in that case what you need to do, we need to take the combination of this attribute with every other attribute, right? This is what I said. But first check which attributes are not present. We need to take the combination of those attributes only because anyway if you take the combination of B, E, F, H, so that will give me this particular closure itself. Okay.
Okay.
Right, for example, let's say here simple example, let's say we didn't get A as A, B, D only, so you don't need to take the combination of A, B or A, D, right, like that. So take the combination of A with those attributes which are not present inside the closure, so then go with AC and AE like that. Okay, so this will save your
So
yes.
if it is CD, then we have to take the combination of D also with other.
So for example like this, right? So what you
Hmm.
need to do, you need to take the combination of CD with A,
A.
CD with B, Oh, yes, that's it. Because every attribute is there. Yeah, only A. Only A is not present, right? Yeah.
Okay, okay.
So first find
So,
out which attributes are not present on the right hand side of any functional dependency. Try to find out the closure. If it is giving R, then that is basically a key. If it is not giving me the R, then find out which attributes are missing inside the closure. Then take the combination of those attributes with that attribute. Okay. Then you will get this particular combination. Okay. So this will you can learn when you practice it. Okay. This will come via practice only. So please try to practice more. And for example, let's say we have this relation R, that's it, right? So we have this relation R, A, B, C, D, and we don't have any functional dependency. In that case, the combination of all attribute will be the key, okay? If any relation don't have any functional dependency, then combination of all attribute will be a key, okay? Because we want unique row inside the table, right? So anyway, combination of all the attributes will be the key here, okay? So this is what it is about the closure of an attribute candidate key. Suppose
Can you repeat that, sir? What you told? Just...
yeah, suppose any relation is not having any functional dependency, right? FD is not present here. In that case, combination of all attribute will be my candidate key. Okay,
So A, B, C, D.
ABCD entire thing. If FD is not applicable to any of this attribute, if any FD is not there. Okay,
Sir, weak entity set don't have key, right?
weak entity set don't have key; it has partial key. So if you see what we say, we have different name for that. I forgot. Something is there. We represent by like this ellipse and this dotted line.
Okay.
Okay. But
Okay.
that weak entity is dependent upon strong entity.
Yeah,
Okay.
the key of strong entity plus.
Okay.
Not plus. So how it's partial key? Suppose we have this strong entity, we have this weak entity. Now what is strong entity here? This suppose you are applying for, let's say, loan. Oh yeah, okay, loan, right? Now you are taking loan from the bank, so all your information will be there in this particular table. So this is basically, let's say, bank, but this entity will be your nominee, right? Now in this relation I cannot store the information of any other person, any nominee who has not taken any loan, right? So this is weak entity set because it is completely dependent upon strong entity, because anyway I cannot enter the information of any nominee unless they have taken the loan, right?
Okay.
So this is what a weak entity set is, and here we have a partial key. So nominee key will be there, nm01 any key, right? But it will be the combination with that particular person as well who has taken the loan. Okay, so that will also be there because combination can be a key. This will cannot possible because person can have two nominees as well, right? Nominee one, nominee two. In that case, this will be act as a key. Okay, because for
Okay.
the same loan we can have multiple nominee as well. So
Hmm.
here you can see this nominee is a weak entity and this loan is basically a strong entity. So who is going to take the loan? Yeah.
Okay.
Okay, that is basically what? Yeah. Okay, we discussed ER diagram. That is not the part. Yeah. But I hope you understand how to find out the candidate key here, right?
Yes, sir.
Now, what is super key? We already discussed. Any combination of candidate key with super key, with any other attribute, that will be super key. But how to find out number of super key here? So we'll discuss number of super keys.
Sir, could you repeat what you said for super key?
So super key is what? So every candidate key is basically a super key. But if you take the combination of candidate key with any other attribute, that is basically a super key, right? Combination of candidate key with any other attribute, that will be a super key. So let's take this example itself of A, B, C, D, E. So I have a relation R, A, B, C, D, E, and our candidate key is what? A. We already find it out, right? Now we know the candidate key. Now I want to find out number of super key. So how we can do that? We know A is key. We also know AB will be key. AC will be key, AD will be key, AE will be key. Similarly, ABC, ABD, ABE, ACD, ACE, ADE, like that. So all these are the possible super keys, right? But we are not going to find out like that. So there is some formula to determine that. Anyone knows that formula?
Yeah, that
To
is
the
the
power
number
n
of
minus
subsets
n.
from formula.
To the power n minus n. What is n here? What is m here?
Number of
N is
attributes,
Number of attribute in relation.
attributes in relation, and n is number of attribute in candidate key.
Yeah, m is basically number of attributes in candidate key.
There can be multiple candidate key also.
Yeah, so we'll come to that example as well. Yeah. So this is how we can find out number of super keys. Now first one is case one. What is case one? We have only one candidate key. So here candidate key is basically only one, that is basically A. Now in that case, what is the formula? Simple, number of super keys what? 2 to the power n. N is what? 5. M is what?
5,
Only 1. So that will
1.
be what? 16 to the power 4, right?
Hmm.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then again, combination of all 4 attribute, 5 attribute, that will be consist of 16 things, right? So here we'll get 16 super keys for a one candidate key A. Now second case, suppose we have two candidate key A and B. A and B. Okay, let me write it down in different. A, then we have and B, not together. A and B are both different candidate key. Now in that case, how to find out number of super keys for relation R?
So it will be 2 raised to n minus m
N minus 2
5, yeah,
minus 2.
5 minus 1 plus 2 raised to 5 minus 1
Hmm.
minus 2 raised to 5 minus 2.
Why we are doing like that?
So this one is from the number of subset, but you can like think about this like, so A will generate this many keys, B will generate this many again 2 raised to 5 minus 1, and they together their intersection will have 5 minus 2, 2 raised to 5 minus 2, that we have to subtract it. So we get
Yeah.
A plus B minus A intersection B.
A intersection B,
The
union
so
B.
if they, yeah,
Yeah.
but the common part with A and B both will generate,
Hmm.
that will also come in the super key also.
Yeah.
So we have to subtract those many super keys which
So
are generated from AB.
okay. So first we are finding out using A. So we got this much combination. But from B
Hmm.
also we will get AB,
Hmm.
ABD, and
Hmm.
ABE also na, in the case of B,
Yeah.
right? But those are
So
getting
these are,
replicated here. So we need to remove those things, right?
yes.
So how we can do that? First, I'm going to find out number of super keys using A. So that will be what? 5 minus 1. Then plus number of super keys using B. That will be to the power 5 minus 1 as well. Minus this combination we have to remove. That will be what? Number of super keys using A union B. Whenever I say A union B, so A and B are both different set of attributes which are the candidate key. Okay, so we'll discuss few more example here. So here together, right, that is AB as a
Hmm.
combination, so that will be 2 5 minus 2, so that will be 16 plus 16 minus 8, that will be 24. Okay,
Yes.
Can you explain it again?
suppose we
So
have
can
two
you
candidate
elaborate
key.
like the
Yeah,
expansion of each one?
yeah. So first we have two candidate. Okay, is this clear? Case one.
Yeah, that's
Yeah.
Yes, sir, that is clear.
In case two, what we are
Yes.
seeing, we have two candidate key, CK1, CK2. Now, number of candidate key using both the candidate key, that is what we need to find out. So, CK1 intersection CK2, right? So, if you apply that formula, probability, it will number of candidate key using CK1 plus number of super keys using, sorry, CK2 minus number of super keys using both CK1 union CK2, right? So, this formula you can remember, okay, for two candidate keys. Number of candidate key using CK, number of super keys using CK1, number of super keys using super keys using CK2, and number of super keys using CK1 union CK2. Okay, so please remember this formula in the case of
So
uh,
it is the intersection.
Yeah, this is intersection and this we are union. Okay.
For to find the number of super keys, it is the intersection of the candidate keys.
Yeah, together we are saying CK1
Yes.
and CK2 both. Okay, so just apply this right.
What
Right.
if there are more than two candidate keys?
Suppose we have three candidate key. In that case, you need to apply that formula. So if you remember A intersection B intersection C, then number of A plus number of B plus number of C, I think minus A union
Minus.
B minus A union C minus B union C. Again, we have plus or minus. You can check.
S-
We have
this is the union. This side should be union, and that will be intersection.
this side will be union. That way will be
Like N union, N of A union, B union, C.
okay.
Um,
So you can apply this particular formula for three combinations, right? But anyway, this will be a complex. We are not going to ask this much, right? So up to two candidate key only you can expect, right? Otherwise, that will be a mathematical question, right?
So one question here.
Uh,
Since you in the case two you have taken A and B separately.
hmm.
So if we have A B together as one candidate key,
uh,
so for that we'll apply the second formula or the first one only.
no, if you are saying only A B is candidate key, right?
Yeah,
Only
yeah.
one key is there, so that in that case, 2 to the power 5 minus 2 will be there. Okay.
Two would be there.
Yeah.
Okay, that only fine.
Yeah.
Okay.
So here
Thank
you can see case 3. Let's say we have two candidate keys. We have one A, B, and then we have B, C, right? Now, in this case, what will be the answer?
2 raised to 5 minus 2 plus
2
2 raised to
plus
5
2,
minus
5 minus 2,
2 minus 2
uh,
raised to 5 minus 4.
1. No,
No, no. How
3.
many key attributes
Union,
are
3,
3,
3.
3, 3.
A, B, C, right?
ABC.
Okay,
Generated
like
from
that.
ABC.
Sorry,
Hmm.
will be 8 plus 8 minus 4. So that will be 12, right? So this much combination you can expect either one key with one attribute or more than one attribute. So anyway, only this will change and n and m will change in the case of case 1. Case 2 also you need to apply this one, and case 3 will be like this when any one will be repetitive, like for example B. But anyway, if you take the union, that is basically number of attributes only, right? A, B, C together. So this is how we
Uh,
can apply. Uh,
yeah, 2 and 3. How do they give the? I mean, if at all there is a ask, how will they differentiate the case 2 or case 3? Will they give us two together or A or B? They will say.
No, no. We'll ask this one. We have this relation R having this functional dependency. Find out number of super keys application to relation R. So first find out candidate key, how many candidate key we have, and then based on that you need to find out number of super keys. Okay.
Okay, sure,
Yeah. Or we can directly mention for relation R, A is a candidate key or AB is candidate key. Then how many super keys are there? Okay.
sure.
Yeah. Okay. So please remember this one. You can easily find out number of super keys. That's it. Okay, so that is basically we have done with this part. What is decomposition? What do you
Breaking
understand
a
by
relation into
decomposition?
smaller relations.
Okay, but how we decide? Suppose I
No
have a
anomalies. If we have no anomalies, like the main reason to reduce redundancy, right? For
yeah.
decomposition.
So basically we do this for normalizing a table, right? Normalization process. Okay.
Right.
So I have a big table R. I want to decompose into R1 and R2, right? But what is our requirement? When we decompose this relation R to R1 and R2, whenever I join these two relations back R1, R2, I should get the original relation back, right? That is what we want. There should not be any loss of information, right? Then how we can ensure that I am going to decompose the R in a such a way that if I join those two relations again, I will get the same relation R. So how we are going to decompose that? Do we have anything for that one?
Three
2NF
rules.
relation.
2NF, 3NF.
2NF, 3NF? No, no.
No, no, three rules, no? R1 union R2 is equal
Uh,
to R.
so we have a condition for lossless decomposition, right? That is
R1 intersection.
decomposition. So first one is what?
R1 union R2 given gives R.
Yeah. So it should cover all the attributes, right? For example, we have this A, B, C, D, E, F. So if R1 is covering A, B, C, and R2 is covering E, F, right? Doesn't make any sense because one attribute is missing here, right? So first we are checking both relation should cover all the attributes, right? So A, B, C, and let's say it is D, E, F, right? So R1 union R2 should give me R, okay? Second one, yes, tell me.
R1
R1
R
intersection R2 should not be empty.
Intersection R2 should not be an empty set. Now, what do you understand by empty set should not be equals to empty set?
At least one
There should be a
attribute.
common attribute, at least one.
At least
Yeah.
common attribute should be there, right? So if you see this A, B, C, and D, E, F. Now, first condition gets satisfied here. But can I join this relation back? R1, R2. I cannot join because no common attributes are there, right? If I try to perform the join operation between R1, R2, I will get a cross product. So combination of one row with every other row, right, from this R2. But that is not my original relation, right? That will be a lossy decomposition. So I don't want that. So how we can ensure? By this condition, there must be some common attribute. What is third condition?
That common attribute must be a key in one of the table.
Yeah. So R1 into R2 either determine R1 or R1 intersection R2 should determine R2. It means what? If I combine these two, so that common attribute must be a key of either R1 or R2, right? That is what we can say.
Candidate key or just a key?
Just a key. Okay, candidate key, super key, doesn't matter. So it should be a key of either R1 or R2. If these three conditions are getting satisfied, then we can say our decomposition is lossless decomposition. Okay. So this is
But I think in the video it was mentioned candidate key, sir. No?
no any key. Okay. Uh, but candidate key is also super key. Okay. Do we have any question? Yeah. So here you can see this question number 4. But here we discuss about when we decompose R into R1, R2. That is what we followed here. But let's say we have this one. R is this much. Functional dependency is given. And we are decomposing it into R1, R2, R3 like that. Number of small relations. So in this case, how to check? So first tell me why option A is not correct here, because anyway we know option C is correct. But why option A is not correct? How to solve this question? Yes, anyone?
Sir, R1 and R2 doesn't have anything in common.
Okay.
First we should check if they are keys.
No.
No?
So
Not.
first check for this condition. R1 union R2 union R3, whatever the number of relations we have, R5 or Rn, that should give me R. Okay. So every attribute should be covered, right?
Hmm,
So A, B,
that
C,
is
I,
true.
J, A, B, C, I, J, D, E, F, G, H. So all attributes are getting covered. This is the first condition you need to check. Second thing is that consider any two relation such that there must be some common attribute. Either R1, R2, R1, R3, or R2, R3. Take any two relation having common attribute.
R1 or 3.
Yeah. We cannot take R2, R1, but we can take R1, R3, right? Because
I is common.
I is common,
Okay.
right? So if I take R1 intersection R3, we got I as a common. Now if I take the closure of I should get either R1 or R3. So are we getting that? Take the combination of I here?
No.
No.
That is still the union of R1, R3 and intersection of that with R2 is still don't have any common attributes. So that will contradict the second condition.
Yeah. So here if you see from this one, we are not getting any common we are not getting any R1 or R3. It means what? After taking this two combination also, we cannot join these two tables, right? So anyway, we cannot join with R2 because we don't have anything in common, right? So this is a lossy decomposition. Okay, this is not getting
So
satisfied.
we should get either R1 or R3
Yes,
when we do the closure of I.
yes. Okay. And if we are getting R1 or R3, then we can say we can join R1 and R3. Then after joining R1 and R3, then check with R2, combination of R1 3. Okay.
Sir,
Okay.
intersection condition is like R1, R2 not equal to null or
Not
empty
equal to
set,
empty
we can
set.
say.
Yeah.
Empty set.
Yeah.
So here we have three elements, R1, R2, and R3.
Huh.
So we have to check whether R1 intersection R2 giving me an empty set or not.
No,
Then
no.
R2 giving,
Huh.
it's not like that.
Any two sub relation you can check. Okay. R1 either R2, R1 or R3 or R2 R3, right? So this
So
condition
R,
is there for decomposition part, right? For normalizing the process, right? But for checking purpose, we generally see which attributes, which relation we are having common attribute. Then we consider those attributes only.
okay.
Yeah. So you are saying R1, R2. If I consider, we don't have anything common, right?
Yes, sir. So in that case only we can left this option.
No, no. Check for R1, R3 as well. Okay.
Okay.
So here
If
we are
one of
just
them is not
using.
having, then it's considered as a loss, right? I mean, it's not
No,
correct,
no,
right?
no. That is not correct.
Sir, but we can mark out this option if R2 don't have intersection with R1 and R3 both. So in that case, R2 won't be able to join with any combination of R1, R3.
Huh, that you can say because R2 we don't any common with either R1 or R3, right? Yes.
Hmm.
Okay. What about this option number two? Can you try now? What is the first condition?
Union should be R.
So is it there? Union is R,
Yes.
Yes.
right? Right. So that is getting satisfied. Now which two relation we have to take?
R2 and R4.
R1 I can take with no. R2, R4 I can go. That's it, right?
Hmm.
G R3 and R1 are isolated, so they won't be
You
joined.
see R1, R2, R4. If you see here, D is common attribute. But if I take the closure of D, what I'm going to get?
R4.
From D, I'm going to get Dij, right? That is basically R4. It means what? I can join these two relation. So I am going to do that. Say R24 is new relation such that R2 union R4, right? So we are joining these two relation. That will give me new relation R24. That will be what? D, E, F, I, J, right? Now check with R2 for intersection R1 or R2 for intersection R3. Do we have anything in common?
No.
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 So that's it. Option 2 is also not correct. Check for option number 3.
Obviously, first condition satisfied.
Yeah. Now which two relation we have to take?
We can take
There
R1
are
and
many.
R2 together,
Huh?
and um, R1 and their combination we can take with R3.
R1 with
So
R2 also
But
we can do. R1 with R3 also we can do. Right?
mhm.
R3, R4
R2,
also we can do.
R5,
Yeah. R2, R5 also we can take, right?
yes,
So here
sir.
we have different options that we can do here. So let's take any two decompose a relation. So let's say for example R1 intersection R2. That is what? A here, right?
Yes.
From A, am I getting R1 or R2?
R2, AD.
Yeah. That is basically what? R2 here. So I can join this R1 too.
Sir, but the closure of A will be A, D, E, I, J.
Yeah, that is fine. A,
That's
D,
fine.
E, I, J. But we are already getting R2 na here.
Okay.
Yeah. So see, why we find out the closure? Let's say A closure is this one. A, B, C, D, I, J. Okay. So from this, what I can say? From this, I can say A can determine B, A can determine C, A can determine D, A can determine B, C, D, I, J, A can determine any combination of this attribute, D, I, J or I, J. That's
Yes.
what I can say from this closure, right? So whenever in the case of any attribute or set of attribute, you are getting anything. So that attribute or set of attribute can determine all the attributes from right hand side in the closure, right? Individually or combined as well. So basically, you are just simply applying the union rule here like that. Okay. So yeah, so here we can join R1 and R2 back. So let's say R12 is what? R1 union R2. So that will give me what? A, B, C, D, E. Now check with R3. So R12 intersection R3. What is there? B.
B.
From B to
B determines
R12
BF.
or R3, which we are getting
Yeah, R3. B determines F. So
here.
B determines BF.
So that will be BF, that is anyway R3. It means what? I can join this R12 with R3. So we'll say R123 is basically what? R12 union R3. That is A, B,
A, B, C, D,
C,
E, F.
D, F.
F.
Right? A, B, C,
Hmm.
D, E, F. Now R123 with R4. Do you have anything in common? Or R5? Yes.
F and D with the R5.
So we can take any one. Okay. Let's say instead of 4 will go with 5. Okay. Now if you go with 5, then in that case D is common, right?
Yes.
Again from D I will get Dij R5.
Yes.
Again I can do R1 2 3 union R5. So R1 2 3 5, in that Ij will get added here. Now I left with only R4 with R1 2 3 5. So in that case F will be the common, but anyway from F I am going to get R4. So here I can join all the relations back to get the original relation. Okay.
Yes, sir.
So that
Understood.
you can take it. So we have a tutorial on this, so you can watch that tutorial also.
I have a question. All keys are super key.
Yes, all keys are super key. Yes.
Okay.
Okay. But reverse is not. Every super key is not candidate key, right? Every candidate key is super. Okay. So this is about the decomposition part. Anyone any issue with the decomposition part? Any question?
So this was the checking, but how to decompose? Like, if we have to decompose, so do you have the example for that one?
Yeah. So in the previous session of week 6, we have discussed one example, practice assignment question number 10. We have decomposed that R to all the way till BCNF, right? So why we are learning this all this concept, decomposition part, then closure, candidate key. In that we have discussed this one. Okay. So please watch that uh, session. Okay. So it around
Okay.
20 minutes we have spent on that particular question. So you can watch that
Okay, sir.
entire thing. Yeah. It will take time to explain now. Just go to week 6, I think, session 2, Saturday session. Yeah. Okay. So this is about the decomposition part.
Sir,
Now,
sir, how to identify 4NF?
okay, we'll discuss after this normalization part, but first we'll discuss uh, what
So
is the
one question regarding this decomposition. You said that we had done till BCNF, right? So after that, we won't be asked to decompose for an F or something.
4NF is basically a no multi-value dependency, right? So it deals with MVD.
Yeah.
Yeah.
So
So
we won't be asked, right, to decompose till there if we have if we want to go till 4NF.
yeah, you can simply check, right, if MVD exists or not. If MVD exists, then it is not in 4NF. That's it.
Okay,
So how to check whether
decomposition won't
MVD
be asked.
decomposition? No. So anyway, it will be a MCQ question. Na? So anyway, you can eliminate the option by checking MVD is present there or not, right?
Correct. Yeah.
So I have
Okay.
explained that decomposition process to understand the concept, right, in detail. In quizzes, in exam, you can simply go through the options. That will be easier. Yeah.
Okay, sir. Fine.
Sir, this recording, this has been recording or not? Because many of the weekly session, the recording is not available in the calendar.
No, no, it is there. So you can check our YouTube channel, DBMS. All the sessions are there.
Okay, sir. Okay, sir.
So I am pasting the link of this today's session. You can go through that. Yeah, I think someone has already pasted. Yeah. Okay, great. So one concept, important concept from week 5, that is basically dependency preserving, right? Now let's say, for example, I have decomposed this one R into R1 and R2 like that. Okay, but there will be some functional dependencies also not applicable to this R, right? So how we are going to do that, right? We should make sure that we are decomposing the relation in such a way that all FDs are preserved, right? So how to check whether all FDs are preserved or not after decomposing? For example, if you see what we have discussed in the case of this decomposition, where it is here. So all the FD must be preserved here, whatever is there. So if you see ABC will applicable to this, BF applicable to this, IJ applicable to this, AD applicable to this, F applicable to this. So all dependencies are getting preserved, right? But we'll see. This will not be case in every question, right? So yeah. So we'll discuss it here. So,
Sir,
huh?
dependency must be preserved in at least one relation, right?
Sorry,
Or every
not it.
relation. Like I decompose into four relation,
Huh.
and one attribute which is contained in three sub-relations.
Okay.
Now that attribute have a functional dependency, so that dependency must be preserved in at least one relation or all the relation that have that attribute.
No, no. Any one relation. Only dependency should get preserved. That's it. It should be there.
Okay.
Yeah. Okay. Yeah. So let's say we have this A and this R and R1 2, right? R1 and R2. Now first we need to find out all the applicable functional dependencies to R1, all the applicable functional dependencies to R2, right? That is what F1 and F2 is. Now, what when I said all the applicable functional dependencies, what I mean? First, write down the functional dependencies directly from the relation itself. You can do that. Then, by applying the Armstrong axiom. So, if you must know Armstrong axioms in the slides, we have discussed about these axioms, right? So, by using that, you can get few more FDs for this R1, right? It may happen, for example, for this R, what I am saying, A determine B is there, B determines C is there, and let's say then we have D determine like that some FD. But for this case, for this R1, we can directly add A determine D, I can see, B determine C, I can see here. But if you observe by transitivity, I can also say A determine C, right?
Yes.
So that also should be a part of F1. Okay. So all the applicable functional dependencies to R1 you need to write down in F1. Right? But checking for every axioms to fit in, that will be a difficult task. So what you can do, again take the closure of individual attribute like that and just add it here. So for example, A, whatever you are going to get, A determine those things, B determine those things, right? Like that you can see. Okay, so you can simply take the closure of individual attribute and combination of those attribute like that you need to go. Okay, because from BC also will get different combination, other from B and C separately, right? So that thing you have to do that. So for this you can watch the tutorials we have explained in detail, but I will explain this question here. Okay, now first we have given the relation R, we have this one. So for simplicity, what I'm going to write, bike name as BN, bike model as BM, this as BEN. Yeah. Now here Bn determines Bm, Bm determines Ben, Ben determines Bn. Okay, I'm just writing it down like that because I don't want that entire spelling here, right? So if R is decomposed into this one, then decomposition is. So first simply check for lossy or lossless. Tell me it is lossy or lossless. Anyway, it is mentioned, but it is correct or not?
Lossless decomposition.
Yeah. So what is R1 union R2 satisfying all the, yes.
Hmm.
Any common attribute is there?
Yes, bike model.
From bike model, are we getting R1, R2?
R2.
Yeah, R2 we are getting. So it is lossless decomposition, that is for sure. But how to check for dependency preserving? Now here first find out F1 and F2. So directly I can write it down bike name, bike model. I will write it down here. Bike name determine bike model. Here I can write it down engine number, sorry, bike model and engine number. But what about this FD, bike engine number, bike name? I cannot add directly here and here. Then what about this? Tell me. So all the FD should get preserved. So this is getting preserved. This is getting preserved. What about this one? Yes, anyone? How is getting preserved? Tell me.
So bike model determines bike engine, and bike engine determines bike name. So bike model will determine bike name from transitivity.
So as long as that relation has attributes from FD and its set space, then it's dependency preserved.
Yeah. Okay. So first write down all the applicable functional dependencies. Can we add few more functional dependencies F1, F2?
Yeah, bike model to bike engine number in F1.
Bike model to bike engine numbers also applicable there for a bike name, because if you take the closure of bike model, so engine number, but from engine number bike name, so we can write like this. Similarly here bike engine number determines what? Bike model, right? So first write down, find out all the applicable functional dependencies of F1 and F2. Then take F plus. What is F plus here? F1 union F2. Okay. Then check for those FD which is not preserved. So whatever the FD we have, let's say B determine E. Then take the closure of B based on F plus, means this union thing, and see whether you are getting E in that particular closure or not. That's it. This is the simple process. So we have R1, R2. First find out F1, F2. Then find out F plus, that is F1 union F2. Then whatever for dependency you are checking, for that you have to use F plus. Okay. So this is how we can do that. So if I apply that concept here, so F plus will be what? F1 union F2. It means all four FDs will be there. If I take all four FDs, what I want? Bike engine number determine bike name. So if I simply take the closure of bike engine number based on F plus, basically both the FDs, so simply I can take BEN. From BEN I can get BM, and from BM I can get BN, like that. So I can say from BEN I can get BN, like that. Okay. So here that's what
Sir,
preserve. Huh?
you write bike engine number to bike name in the F2, right? What's written? Bike model?
Bike BM, bike model. Yeah.
Okay.
But why are you checking for bike engine determining bike name?
Because this is not getting preserved. Now this one. First is getting preserved in R1, second is getting preserved in R2. Where to check, where to preserve this FD? This is remaining now. For this FD only where I have to check. Otherwise all are preserved.
But in F1 you have written bike model determines bike name.
Yeah. From
So
here you can,
bike model determines bike engine number also. So bike engine number will determine bike name.
yeah, that here we just have three FDs, so that's how we can easily determine. What if we have 6, 7 FDs, right? In that
Okay.
case, it will difficult for you to understand, right? How it is getting applicable. So for that, you need to apply F1, F2, find out the all the functional dependencies, take F plus, and then take the closure of that particular FD here, right? And see whether you're getting that thing or not.
Sir, in the
Hmm?
functional dependency set, we cannot write a functional dependency which include attribute which is not a relation, right? Like in
Sorry.
the F R2, in the F2, you cannot write a functional dependency which includes bike name.
No, no. It is not applicable, na. Attribute is not present.
Hmm. Okay, yeah.
So for dependency preserving, we just need to check the decomposed relation. The FDs of the decomposed relation have all the attributes, right?
Yeah, FDs of decomposition relation. So, but first we will find out all the applicable FD. So here we can directly write down from this. but all the FDs we need to find out applicable one. Okay.
So then we can suppose if an FT has an extra relation and that attribute is not present in the decomposed relation, we can ignore that, right? So
Yeah, we can ignore that. We cannot add that. So all attribute
yeah.
must present there.
Okay.
So
Sir, that closure of bike engine, the bike engine plus you have written, you'll you'll find whether it is a key.
hmm,
At the end, you're
here like
finding the closure of bike engine. Why are you doing?
because I want to check for this FD only. Okay. Rest all are preserved now. How I am going to check? Take the closure of left hand side. If right hand side is present inside the closure, it means this attribute determining this one.
Okay,
Okay.
so you'll check whether it is determining the right hand side.
Yes. Uh, Let me open one slides. Week 5 only. In that very good example is there. Where is that concept? Loss? Let's join that dependency preserving. Yeah. So if you check the lecture 5.5 slides, let me open that. In that, this entire thing is explained. Here we just have three FDs, so that's why. Is this visible?
Yes, sir.
Yeah. So here you can see this example, right? We have this relation R, this much FD, decomposition is there, right? But we can see this is getting preserved in R1, this is getting preserved in R2, this is getting preserved in R3. So we left with this FDs. I cannot add this FD directly to R1, R2, R3 because A is not present, AF is not present anywhere in those three. So we need to check for this one, okay? So for that, what we are doing, we are finding out F1, F2, F3. So all applicable functional dependencies to R1. So here you can see this one, A determining A, B, C, D, B determining B, C determining C, determining like that. Then combination of two attributes. Then go for three attributes. Go for four attributes. Four attributes anyway we have four attributes only. So three attribute like that. Okay. So this is how you need to find out first. F1, then F2 like that, F3 like this, and then take F dash that is basically or F plus basically F1 union F2 union F3 means all these three F days. Then check for each of these that is not getting preserved. So check A determine E. So take the closure A plus based on this one. So here you can see we can find out. Similarly for AF, take the closure based on F dash. Similarly, take the left hand side for every FD and check whether you are getting right hand side or not. But based on F dash. That is basically F1 union F2 union F3. Okay. So this is the example like what we have discussed in lecture. So that was easier one. We can easily find it out. But here we required thing F1, F2, F3. We cannot do this directly. Okay.
Sir, in F2, why B doesn't define B? F defines F is written. Why
Sorry.
not B? B defines B
Here
in F2.
F2. Yeah. So B determine F na. So anyway, we can add this B determine BF also, right? Same thing. Because B determining itself na, we can do that. Okay. So please follow the tutorial and please try to solve this example and this example as well. Next example. Okay. Try to take this to one and then simply solve the question without looking at these slides. Okay. So check for dependency preserving part. So this is about the week 5. That's all we have. Then if you see, yeah, FD equivalence, right? So equivalence of FD is there, canonical cover is there, but FD equivalence is that same thing, right? So what is FD equivalence? So let's say we have two functional dependency F and G. Whenever I say F covers G or G covers F, what does this mean? It means that F cover G means what? All the FDs in G I can determine using F. G covers means what? All the FDs in F I can determine using G. Okay, this is what F covers G and G covers F. But both the things are possible. Like for example, F covers G and G covers F. Then we can say F and G are equivalent. Okay, that's what equivalence concept is. So first check for F covers G, then check for G covers F. If both the things are correct, then it will, then we can say F and G are equivalent. Okay, this is what the concept of FD equivalence is. Okay, so we can simply check for those things. That's it. Okay. Now this is for week 5. Dependency preserving is also done. In week 6, we already discussed in the previous sessions of week 6. But anyway, we discuss week 6, that is normalization.
Sir, one doubt.
Yes.
Sir, can you explain that extraneous attribute?
Okay.
Because that questions are like quite confusing actually. Because in some dependency cases and all, lossless and dependency preserving also, we have to apply that axioms. So extraneous
No, that
attributes
extraneous attribute is
are
there for checking canonical cover, or we can say
so,
minimal cover. Okay, that concept applicable to this one, minimal cover. Okay, so why we find out canonical cover, minimal cover? Suppose we have big F like that, what we have here, but you can see few FDs are redundant here, right? So it is not required like that. Okay, so in that case, we need to remove those FDs. Okay, so how we are going to remove, how we are going to check whether FDs are redundant or extraneous attribute is there? For example, I can say A determine BC, right? Then I can say B determine C also. But anyway, I don't require C here, because from A determine B and B determine C, I can say A determine C, right? Then why this C is there? So this is how we can find out. We can reduce this FD to a minimal set. For that purpose, we use canonical cover, and for that process, we follow that extraneous attribute, right? So for example, we have this functional dependency. Let's say A B determine C. Okay, we'll take any example if it is there. So here is the concept of canonical cover, but for that you can simply check for equivalence, whether F and FC must be both equivalent. Okay, so F cover G, G covers F. That thing you can check here, right? But here you can see we can find out some extraneous attribute as well. Okay.
So your voice got broke. Can you please repeat what you just said?
For this question for canonical cover, both the FDs must be equivalent. So this F and this canonical cover F or minimal cover both must be equivalent. So you can check for those conditions. F covers FC and FC covers F. Okay, in this particular case. So first, all the FDs from F should be able to determine from FC, and similarly, all the FDs from FC should be able to determine F. So both the things you have to check, and then you need to check which option satisfying that thing. So A and D will get
so if
satisfied. Okay. Huh?
so if we take super key from F and FC also, it should result in same set of attributes, right, sir?
Yes, yes. Yeah. Let me.
So one question.
Huh?
Um, in the example which you just took for extraneous attribute, uh, the two FDs were A determine BC and B determine C, right? So instead of considering C as an extraneous attribute, what if we don't consider the second FD at all? So the
Yeah,
minimum cover would be just one, no?
just one. Yeah. So in that case, that will be redundant one where I have written that. Yeah, that is correct.
Okay.
So we need to remove redundant FD as well. Yeah. Let me check. I think it is there in lecture 5.4, I guess.
Because we can
5.
decompose and get A determine C also.
Hmm. I guess extraneous is there. So So there are two things. Either attribute can be extraneous on right side or left side, right? Both the things are possible. Okay, this one. So here you can see consider a set f of fds. So let's say alpha determine beta. It's a set of attributes. So here we have set of attributes. Here we have set of attributes, right? Now I want to check attribute A in extraneous in alpha. So here we are checking for left hand side first. For example, A B determines C. So on the left side, either A can be extraneous or B can be extraneous, right? So we need to check that which attribute is extraneous. Extraneous means what, as name suggests, extra, right? So without using that attribute also, the FD will get preserved. FD will be safe. Okay. So that is what we need to find out. But how we can check in the case of left hand side? So first remove that FD from the F. So here we are removing that FD from F. Then remove that attribute. So for example, I am checking for whether A is extraneous or not. So I remove that A extraneous or not. I have added B determines C in FD like that. Okay. So for which attribute you are going to check, you have to remove that from the set, and then you can add that FD inside the F, and then check for whether A is extraneous or not, right? So attribute A is extraneous in beta if A belongs to that particular right side, right? And the set of F, this is like that. Logically implies F. So here for left hand side, and here it is for right hand side. Okay, we are going to check. Same thing we have to follow on the right hand side as well. Simply remove that FD, then remove that attribute for which you are checking, and then you can consider that remaining FD inside the that particular F. And then see, take the closure of B whether you are getting that A in that closure or not. Okay. So for example, you can see here A determines C, AB determines C. Now here we have A, B determines C. Either A can be extraneous or B can be extraneous. I don't know, right? So first we'll check for A here, whether A is extraneous or not, right? So if I remove this FD from F, remove A from F, I left with B determines C. So I'm going to add A determines C and B determines C, right? Now whether B determines is extraneous or not, how we are going to check? Suppose in the case of B closure, if I'm getting A, then A is extraneous there, right? That is what we can say, I guess, right? Or without using A, if you are getting C, then also we can say that is that A is extraneous here or not, right? But here in this case, we are not getting that thing. So if I take the closure, yeah. So here you can see A, B is extraneous in A, B determines C, because if I remove B, anyway I'm going to get that FT, right? So A, B determines C logically implies A determines C. That is the result. Yeah. So here B is extraneous, we can see, because we already have A determines C. A is not extraneous here. Okay. Because anyway, if you see this A determines C, I can add any attribute. I can add M here, both the side. Like that we can do, right? That is the case here. I can add any attribute on the both the side. That is what augmenting is. Augmenting, yeah, augmentation. Right? And by using decomposition rule, we can write like that. So this process you can follow for left hand side and right hand side. Here you can say. Simply remove that FD from the F, remove that attribute for which you are checking, add those remaining FD inside that at F plus, and see whether getting preserved or not. Okay, that's it. Same thing for right hand side we have to do. Okay, that's it. So you can see this here. It is given to us. The equivalence FD is also there.
So,
Canonical cover is
so in the
also
previous,
yes.
so in the previous example, that yeah, A to C, A B to C, we can remove that A in second one, right?
Yeah.
Why are we removing B?
No, we cannot remove A here. If I remove A, then this will not be the correct one. Now B determines C, that is not a correct FD here, right? A B determines C, not B determines C here, right? So A is not extraneous here.
So if something is
Okay.
extraneous on the right side,
Hmm.
how do we check it? You said for right side.
For right side, it is simple only. For example, here you want to check for this one, right? So right hand
Yes.
side is simple. Remove that attribute for which you are checking. For example, C. Okay. So that's it. Add that remaining FD inside the functional dependency. Anyway, we have added by removing C. So I got two FD here. A determines C and AB determine D only. Now take the closure of left hand side and see whether you are getting C in that closure or not. For which we have checking. If I take
Okay.
the closure of AB, so AB determine D, but from A I'm also getting C here, right? So
Yes.
anyway, inside AB closure, C is present, so C is extraneous here.
So
Okay,
for left side also we have to do the closure only.
yeah, but left hand side also we have to do, but yeah, in that case you need to check whether what we can say,
If we remove B, we have to check the closure of A.
if
So
we
then in first example, that A plus is missing. We don't have B in that closure, right? So, but we should have B in the closure.
where here only A determines C is there, na? That's it. Now by augmenting, you
But
can add B on both the side like this. Any attribute you can add. Augmentation, if you remember.
okay, sir.
So any on both the side we can add the same attribute like that. But by decomposition rule, I can write like this: AB determines C and AB determine B, right? If I apply a
Yes, sir.
decomposition rule, yeah. So this is what we are getting here. Same thing, right? Anyway,
Okay, okay.
yeah,
So sir, left side also, how do we check? We have to check for closure.
yeah. So left hand side check for the closure part. So here that thing is only two FDs are there, but check for this one. Suppose uh, in this case it is there, but if we remove that attribute, then if we want to check for extraneous of A, take the closure of B, you should get A inside that closure. Okay, but here we are not getting A, so
Okay.
in this case, okay, so A is not extraneous here. But if you observe, if I take the closure of B here, but anyway it is A determines C is there, right? So we don't have anything here. So here it is simple one. That's why we are not getting that. But if you look at any different example, let me check.
No, if you check B is extraneous, then we'll get the closure of A.
Yeah, A determines C only, right? So
Yes,
here we just have
but
two
B,
FPs. Yeah. So see, on the left hand side is complicated, right hand side is easier. Simply remove that attribute, take the closure of left hand side. If you are getting that attribute, it is extraneous. If you're not getting attribute, not extraneous. So here we are getting C. For D, I am going to remove D. Now check for A, B closure. Are we getting D inside that? No. So D is not extraneous. That's it. But for the left hand side, what you need to do, let me take a different example here. Uh, left hand side, na? Yes. So here we have R, here we have F combined set is now this one, okay. A is extraneous and A, B determines C. It means what? Without removing this also we are getting that thing, right? So if I do like that, A, B determines C, we need to check. Now, if I take the closure of B, implies on dependency effect we already present. Here also same thing is there. B is he already present, so that thing is not applicable because anyway both are the same empties only, right? I can augment that thing. So in some cases, what will happen? This is easier. Previous also easier because we can directly look at the FDs. But remove that FD or remove external attribute. Take the closure of remaining one and see whether that attribute is there inside the closure or not. You can check that. Okay. Same thing. What we are doing for right hand side. Here anyway, we are seeing this one is there, right? So simply we can remove that FD. Okay. Left hand side is little bit complicated. Remove that one closure, one attribute. Take the closure of remaining one and see whether you are getting that attribute or what we have removed, right? From this one. Otherwise, same FD
if
will
we don't get it,
then that is not extraneous. Okay, that's what we can say here. Here, but anyway, here we are saying that one, right? Extraneous, yeah. Okay. So left hand side, because we cannot apply any decomposition rule to left hand side, right? AB determines CD. It means what? AB determines C, I can write. AB determines D, I can write. But it doesn't mean that A determines CD, right? This is not correct. We cannot decompose this left hand side, right? That's the case. So simply remove that and see whether we are getting this or not. So after deleting A from AB is implied that other dependencies. In fact, B determinacy is already present here, so we can remove that, right? So anyway, this will be redundant, so we are removing this one like that. So only this thing will be there. Okay. So try to solve few examples. Just watch the lectures. I think Professor has explained here. I think in this also it's basically a finding of candidate key. Okay. Okay. So just go through this slide. That will be good enough for extraneous attribute. But anyway, we are doing this process for finding what? Canonical cover. Okay. So we are doing this for canonical cover. Here you can see F logically implies all dependency in FC. Similarly, FC implies F, then we can say it is equivalent. Okay. It is minimal set of FDs equivalent to F, no redundant FD, no redundant part of FD. So for this two, we are checking the extraneous attribute. That's it. Okay. Okay. Good. So we can just go through the lectures that will be available. Now, important concept of normalization. Okay. How many normal forms we have? Just tell me, and how many? What are the conditions? So just check that. I will just come back in 2 minutes. Okay. Yeah. Okay. Yeah. So tell me, what are the normal forms we have? Yes. What are the normal forms we have?
So
1NF.
1NF,
1NF. What is the condition for 1NF?
atomicity
All
No
of the
the like
multi-value
domain.
attributes.
Atomic values. It means what? No multi-valued attribute here. What is multi-valued attribute? Yes, anyone?
Attribute which can hold more than one value, like a phone number.
Right. So in ER diagram, we represent by like this, right? Double ellipse. What
Does
about
it mean composite?
not composite? Composite is different. So here, let's say in a particular column only, we are storing both the phone numbers 999, comma 89 like this. Multi-year attribute, right? There
Okay.
should not be anything like that. All are atomic values, only single values are present inside us. So anyway, in the question, if we mention consider all the atomic values or no MVA, it is in 1NF, or you can assume that, always assume it is in 1NF, unless we have mentioned that it consists of MVA. So assume in 1NF if no information is given to you. Okay. Now what about 2NF?
It should be in 1NF first.
It should be in 1NF first, then
No
And there should
partial
not be any
dependency should
partial
exist.
dependency.
no partial dependency. What do you understand by partial dependency?
A
Like
proper
if
subset
AB
of the
defines,
The right side should not be a subset of a candidate key.
Yeah.
a
So if you say
non-prime
this,
attribute should not be a subset should not be determined by a proper subset of the candidate key.
yeah. So if we have this FDX determine A, and where A is, for example, non-prime attribute, and X is what? Subset of candidate key here. If this is there, then this is what partial dependency is, right? So subset of candidate key determining non-prime attribute is what candidate key here. For example, we have A, B as my candidate key and rest E, D, E of our non-prime attributes. And if B determine E is there, so that is basically what? Subset of candidate key determine non-prime attribute. So this will be my partial dependency, right? So there should not be any case such in this particular relation so that it will be in 2NF. So no partial dependency. This is not allowed in 2NF. Okay. Now what
There
is
is
prime?
no
Yes.
condition that the left side should be a super key, no, in 2NF.
No. No. No.
Okay.
So what is prime and what is non-prime attribute? Simple.
Prime
prime attribute are part of
attributes are part of a candidate key.
Yeah, attribute which are part of candidate key. Attribute which are part of candidate key. What are non-prime attribute? Remaining attribute
the
apart from
non.
candidate key, right? Yeah, remaining attribute apart from candidate key. Okay. So first find out candidate key. Second find out prime attribute and non-prime attribute, and then you need to check for this particular conditions. Okay, this is for 2NF, no partial dependency. What about 3NF?
A non-prime attribute should not determine another non-prime
Yes.
attribute.
What is that?
Transitive dependency.
No transitive dependency. Right? It means what? NPA determining NPA should not be there. If it is there, it is basically transitive dependency, right? This is not allowed in 3NF, but it should be in 2NF. It means what? It should be no partial dependency, right? So it should be in 2NF, 1NF as well. Then also it should have no transitive dependency. Okay, this is what 3NF. What about BCNF?
Non-prime should not determine a prime attribute.
Non-prime should determine prime attribute.
Should not.
All the functional dependency must have a
The left side should be a super key.
So
Yeah. So left hand side of all FDs must be a super key, right? It should be a super key. So left hand side of every function dependency must be a super key for BCNF. Okay. But it should be in 3NF, 2NF, and 1NF first, like that.
In 3NF also left side should be a super
Yeah.
key, isn't it?
It's so anyway it is in BCNF, it means what? 3NF is basically like it will be in 3NF as well, right? Or left hand side is super key. You can see anyway it is in BCNF. Yeah. What about 4NF?
sir. So how 3NF is different from BCNF?
In BCNF, we are not allowing anything, right? So left hand side
We
must
are
be a
not checking for transitive dependency, no, in BCNF.
no. There should not be transit dependency because it should be 3 ENF first, right?
Oh,
Yeah. So whenever we are dealing with the prime attribute, determine prime attribute, right? This is okay in 3NF, but this is not allowed in BCNF unless this prime attribute is a key, okay? Candidate key or super key. So prime attribute, my prime attribute is there in 3NF, that is fine. In 2NF is also fine, but it is not allowed in BCNF, okay?
Okay.
Yeah. What is 4NF? No,
No, multi-valued dependency.
multi-valued dependency, right?
so I still have a doubt.
Hmm.
How can BCNF be in 3NF then?
So in BCNF, every left-hand side is a key, right? So there is no transitive dependency. Now NPA
So
will
the
not be
other
doing
way
like
is not
NPA.
okay. 3NF won't be BCNF then.
No, no, no,
Always.
no. So this is a higher normal form. So if it is in BCNF, it is already in 3NF, 2NF, 1NF. If it is in 4NF, already in BCNF, 3NF, 2NF, 1NF, like that. Okay. So this is about the normalization. We do have 4NF, no multi-or dependence, right? So we come to we'll discuss this MVD, but
Isn't
first
there any other condition for 4NF?
it should be in BCNF first,
Okay.
and then no MVD. Okay. So I already explained this 4NF in the week 6 session as well. So please watch that entire session. Very useful. Week 6 Saturday session. It is there in calendar. You can check. Okay. But I will again discuss one example here. So
Sir,
let's try
can
to.
you put the link, sir, because calendar is not visible for me.
Okay, I will share
Yes.
that. Yeah. But anyway, if you check the discourse, I have pinned few posts from previous term, so that will be also useful. So that is important link from the previous term as well. You can check that. Okay. So I think week 6 happens on Saturday. Okay, I will check for a week 6 session. I guess this is the one. Yeah, I'm shared the link in the chat. You can go through that link. Okay.
Thank you, sir.
Okay. So let's discuss this question. We have a relation, we have a domain. Atomic values means what? 1NF is already present. Identify set of functional dependence satisfied by R in BCNF. Now, what we discuss about BCNF? Left hand side must be a key for every FD. If it is there, then it's already in BCNF, CNF, 2NF, 1NF as well. So what we need to do in this particular case, for every FD, find out the candidate key for this relation R. And every left hand side must be a key. Okay. So what about option number one? What's the key here for option number one? So first just check the in this case, you can directly check the left hand side for BCNF. Take the closure of ABC. Are we getting R? Yes. Take the closure of AD. Are we getting R? A, D, then B, C. Yes. So here both the left hand side is the key, right? So first option is correct for BC enough. What about second option? Can you get take the closure of AB? Are we getting R?
Yes.
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 This is fine. What about this one?
No.
No.
No, this is also not correct, right? So option B is not correct. What about C? Can you take the closure of A? Are we getting R?
Yes,
Yes.
A to B, B to C, C to D, D to A.
Same here, same here, same here as well. So every left hand side is a key here. So second, third option also correct. Here also this is not getting violated, right? So simple question, just simply check for BCNF left hand side must be a key, right? For every FT. That's it. Okay.
Sir, please repeat this second option.
Second option you can see AB. Take the closure of AB. Yes, that is correct. AB, CD. I am going to get all the attribute. But what about this FD and this FD? this is violating, right? Left hand side is a knee, is a key. So if you take the closure of CD here, I am going to get CDB only, right? A
Sir,
is
we will also get D from
oh,
A.
sorry. A
D2.
also, yeah, this is also correct. Yeah, sorry.
Hmm.
What about this one, last one? Yeah, this is also
Last
correct.
one will fail.
Last one will fail. Yeah, if
Hmm.
you take the closure of D, DA only will be there, right? Like that.
Okay.
If you say B here, in that case, D will be also, this option will be correct, right? Because anyway, from AB, we are going to get C, right?
Mhm.
Yeah, yeah, correct. So simple question, you can check for BCNF as well.
So when you define a super key, so like as you said that it's a combination of a candidate key and some other attribute, right? So cannot we say that the attributes which form a super key are non-prime? Because
Yeah, so
the
you are saying,
attribute,
suppose A is my candidate key and we have other non-prime attribute. So AB will
yeah,
be a super key. Yeah, that is fine.
yeah, so it's a non-prime attribute, na AB together.
No, B is a non-prime attribute, A is prime attribute when A is a key. This is what we are saying, right?
Correct, correct, correct.
Yeah.
So B is non-prime.
Yeah.
Okay,
So in that case, combination will be super key, na? This is fine.
huh.
Yeah. So here, so we already discussed this example, similar type of example in the week 8 session. You can easily solve this question, LRU. Where it is question, where are the questions? 4.5. Okay, only one question on BCNF. Okay. Uh,
Sir, do we have question from week 7 in this quiz too?
week 7, just go through the slides. That will be good enough. Like for which purpose we use such commands, right? So those things only. Just go to the slides for week 7. That will be good enough. Yeah.
Psycho
For
PG2.
week 8, that's magnetic disk plus that what we said binary search tree and plus this LRU, MRU. These are the important topic. Okay, from
Hmm.
week 8. Yeah. And week
Okay.
7, the slides are good enough. That's it.
So this will be discussed in Saturday session.
Yeah, we'll discuss. We'll discuss this entire binary search tree and MRU. But anyway, if you have any doubt, you can ask us at a discussion. Okay.
Okay.
And here we can
Sir,
see this. Uh,
sir, in quiz 2, what will be the percentage of questions from week 1 to 4?
simple one question you can expect. That is like, for example, we can give in SQL, decompose that table. Some FDs will be there. Find out the key like that will be there, right? But anyway, any one question you can expect, maybe, okay, from week 1 to 4, but mostly week 5 to 8 only.
Okay, sir. Thank you, sir.
Yeah. Yeah, so we got one more question. So here we have all deposed to be seen enough, then all depends are preserved, not to be served. Very good question. How to solve this question? Yes, anyone? Who solved this question during the mock test? Tell me, what is your approach here?
Sir, first we will check here BCNF.
How to check this CNF? It's question of dependency preserving. Okay. Yeah. So how to check for BCNF? Again, same question. Check for BCNF. Now, how to find out for BCNF?
Check if all are super keys. Find the super key.
What about N? NP, right? That's it, right?
Hmm.
So not in BCNF.
Yes.
That's so R is in BCNF? No. Option A can be removed. Decompose to 3NF, decompose to 3CNF. Now tell me how to approach this question. First check for second option is decomposed to 3NF but not in BCNF. All dependencies on R can not be preserved. Here we are saying decomposing to BCNF such that dependencies are preserved. We are saying dependencies are in BCNF, then all dependencies are not preserved. Right? So in this case, we need to
Sir, in
decompose.
3NF,
Okay.
sir, in 3NF dependencies are preserved now.
Up to 3NF, we can say up to 3NF, we can say dependencies are preserved, right? But BCNF is not guaranteed that dependency preserved or not preserved. Okay.
We can decompose the whole relation
Then option
into
2 is also wrong
sub-relations.
because it cannot be simultaneously in 3NF and dependency not preserved.
Yeah, you can check that, but yeah, it's better to check that. Okay. Yeah. We generally don't go like that. Yeah. So yeah, it is not correct. You can say, but still you need to decompose till 3NF and check whether dependency preserved or not. Then go for BCNF and check dependency preserved or not. So anyone solve this question? How did you solve this question? Or no one solved this question? Okay. So here what you need to do, we know it is not in BCNF, but first it should be in 1NF, not mentioned, so we assume that 1NF is there. Now check for 2NF because we need to decompose till 3NF, right? So how we do that? First check for 2NF, then not satisfying, decompose based on 2NF, then check for 3NF, not satisfying, decompose based on 3NF. Then check for dependency preserve like that. So if you discuss this example, then all your question out will get clear. So quickly solve this question. First, tell me what is candidate key because we need to find out candidate key, prime attribute, and non-prime attribute. That's it. Tell me what is candidate key here.
Sir, where we can find this session PDF?
Q.
This is a mock test only. I will upload on the right. Okay. Please mute. I'm getting background. Yeah.
Is Q a candidate key, sir?
Is Q candidate key. So first check which attributes are not put on the right hand side. So you can see here PM, PM, Q, and all are present. So you need to check one by one. And if you check one by one, you will get this much as candidate key here, right? M, because from M I'm going to get all the attributes. From Q I'm going to get all the attributes. So I know M and Q individually. Now I left with N, O, P. Take the combination of N, O, N, P, O, P. Check the closure of this one and find out you are getting all the attributes in the relation R or not. So here we know the attributes are what? Here we have this 4 as a key. Okay, so I hope you will find out how to get this candidate key. Okay, so we got this candidate key. Now what is prime attribute here? M, Q, O, P, N. Correct? Yeah. All are prime attribute. We don't have any non-prime attribute here, right? Hello? Is this correct?
Yes, sir.
Then what to do? Check 2NF condition. Is 2NF condition will be there?
Yes, since all are prime attribute, then partial dependency will not exist because there is no functional dependency
No, N to
to
P.
from yeah.
Prime, prime, prime to prime, prime to prime, not prime to prime.
Hmm.
This is key, right? This is also a key. This is also a key, right?
Hmm.
So left hand
But
side is
key
the key
itself
here.
is self. But if we have a key, we can also say that that is also a collection of prime attributes.
Yeah, but that should not be. So when we say prime attribute, so entire key is also we can say collection of prime attribute, right? But here we are checking left hand side is a key or not, right? That's it. Here it is a prime
Oh.
attribute, but it is not a key, right?
Hmm.
Yeah. So if you see for BCNF, which FD is getting violated?
No, we were checking 2NF, no, sir?
Yeah, sorry, for 2NF, which FD is getting violated here? Do we have any FD?
No.
Because because right hand side is not NPA here, right? So there is no partial dependency here. So it is in 2NF. What about 3NF? Do we have transitive dependency here?
No,
No.
there are no non-prime attribute.
Yeah.
Hmm.
There are no. non-prime attribute is in 3NF. Now, can we decompose it to a BCNF? It is in 3NF, but is it in BCNF as well?
No, because
This is fine, but this is not correct, right? Here n determines p, so it is prime attribute determining prime attribute. Left hand side is not a key. In that case, what you are going to do? Tell me how we are going to decompose.
We can break it like
Yeah.
our relation.
How to break? On which basis you are going to break?
We can take out the attribute that is in that NP aside.
Yeah. So whichever the FD voiding my condition, take the left hand side, take the closure. What we are getting here?
It's
Closure of
NP.
n, na, sir.
The closure of n only. Whatever the FD is voiding my that condition BCNF for 3NF condition, take that particular FDs, take the closure of left hand side. So here we are going to get NP here, right? Make this as
Yes.
one relation R1. So we are decomposing this R2 R1, that is basically my NP. What should be my R2? Now here comes the concept of lossless decomposition, because every decomposition must be lossless. Now what attribute should be there? Please try to find out.
P
I will
will be the common. We have to have one
M.
common attribute.
Yeah, MNOQ. N will be common.
first add all the remaining one, because that should be there, right? O
Yeah.
P, not P, O Q M, right?
Also N. I.
So which one, N or P? Because remaining we have added, because R1 union R2 must be R. So we have added O Q M. What about which attribute we have to add?
If
P
we take
not M.
n, then it can be a key for R2, no?
Huh.
So n will be there.
M will be there. Yeah, okay. So just try to solve. I will just start a different session. So I have CT session as well. You can solve. Okay, I have stopped sharing. Just a second. I will just come back in 2 minutes. You can solve this question till then. Okay. Or if you are done with this, you can also solve MVD question uh, in this particular case, right? So, but before that, solve this question. I'll just come back in 2 minutes. Yeah, here we can add n here, that is for sure. Because if I add p here, what will happen? Common attribute will be what? Yes.
P. If you add P, common attribute will be P.
Then will we get either R1 or R2 from that p? Are we going to get R1 or R2
No,
from
no,
that p?
no.
No, right?
N should
No.
come.
Hmm. Yeah. So p should come there, right? So that's why P should come here. So instead of, sorry, P should not come there. Instead of P, N should be there. Now if I take R1 intersection R2, N will be there, and that will give me NP, and that will be R. So it will be a lossy decomposition. Sorry, lossless decomposition, right? Now check for R1, R2, we know NP, and here we know, sorry, N, O, Q, M. Now all function dependents are getting preserved or not. Just check for this one now, or which is not getting preserved, or how we are going to check that. Just check.
OP is not giving Q.
Now, oh, okay, that was visible. Okay, thank you. Okay, so any doubt in BCNF, anyone? Am I audible?
Yes, sir, you are audible. No, no doubt.
So yeah, tell me, any doubt in BCNF? Okay, great. So what is 4NF? What is MVD here? Yes, anyone? Tell me. Very good question here.
MVD was satisfied that big condition that we have to define take four tuples and then select alpha, beta, and the remaining attributes as gamma, and then check alpha 1 equal beta. So alpha
Okay.
T1, alpha of
So
T1.
here we can do one simple thing. We have A multi determine B, right? So let's say alpha multi determine beta. We have one MVD here, right? Now, let's say how we are going to check. So there are few conditions you can check for that. But what we discussed in previous few sessions, just take any two tuples such that left hand side value is same. So alpha value is same. So keep same alpha value, swap two different beta value, okay, two different beta value, then you are going to get two new rows. Now if those two rows are present inside this particular table, then we can say MVD exists, right? So this is what we have discussed, right? And how to check for 4NF? No MVD should present, and left hand side must be a key, and it should trivially determine, right? That is what we have discussed in MVD. So please, you can watch week 6 second session. I have discussed that in detail. Now if you apply that particular thing here, so what we said for MVD, at least how many attributes are required?
3.
What is the condition for that?
Two must be independent.
And two must be independent, right? So at least the attributes are required, two must be independent, right? Then only we can say MVD will be present, right? But suppose any relation is having just two attributes, no need to check. It is already in 4NF. It is in BCNF, 3NF, 2NF, everything, right? If any relation having just two attributes, it is always in 4NF. Okay, remember this point. Now, if you observe this one for MVD, at least three attribute must present, two must be independent, and you can check for this one, right? So keep the same alpha value, exchange to beta value, swap to different beta value. You will get two new rows. If those two rows are present, then we can say MVD exists. Okay. Otherwise, not. If MVD does not exist, then it is in 4NF. If MVD exists, it is not in 4NF. Simple concept. So please watch that particular session. Now, how we are going to solve this question? Does anyone tell me? Anyone solve this question in the mock test? Here is a different approach, but we'll go with a different approach. Both the things are the same. So what this R is giving us? We have relation that is A, B, C, D, E. So 0, 1, 2, 3, 4, 0, 5, 6, 7, 8. So we have added these two rows. Now what about the first thing? How we can apply this here? Tell me. How we are going to apply this here?
Consider 0 as alpha.
0 as alpha, okay. Then yeah, alpha determine beta, right? So 0 alpha. Then what we have to do after this? If MVD is there, right? So applicable is there, right? This were applicable to this R. Now what we are saying here, we need to find out the other tuples which are part of this relation R, but we have just given these two rows, right? So tell me.
What do they mean by A multi-determines B and B multi-determines D? In these two tuples, how can we make out?
Yeah. So either you can apply first one or second one. So but first you need to apply this one, A multi determine B. So what I said, for MVD, keep the alpha value same. So we have this T1, T2. Now alpha value is same. Exchange the two different beta values. So here you can see beta 1 and 5. So I'm going to swap this value. So instead of 1, it will be 5. Instead of 5, it will be 1. Right? Now I got two new rows, 0, 5, 2, 3, 4, and 0, 1, 6, 7, 8. Is this correct? Yeah, we got two new
Yes.
rows, right? By swapping this. So these two rows must be present inside the R to satisfy this MVD. Okay, that is what we have discussed. So we got two new rows here such that this is applicable to this relation R. Okay, so you can see the option. I guess one of the option will be this one. Yeah, option number C. Now I have applied this one. Okay. Now what about this one? How to do that? Yes, anyone? Okay. Did you get what I have done here?
So I have swapped only the B column values, and rest all remain same.
Yes, because we are only first applying A multi-determine B, right? So take same alpha value, swap to different beta value. That's it.
Okay. And these two are present in the option. Okay, okay,
Yeah.
fine.
So these two must be present inside the table. Then only we can say MVD exists. So that's why we are going to add those two rows here. Now we can say this exists now. If you apply those 4 or 5 conditions given in the slides, all will get
Hmm.
satisfied here. Okay.
Yeah.
Now what
So it
about
can
the
be any
second
one of
one?
those, right?
Huh? Yes.
It can be any one of those two, is it? Those two. Basically, we see the second one in the list. It may be the other one also, is it?
Yeah.
Okay.
So we have applied this one, but we need to check for this one as well, now because MVD is satisfied for this both the things. Now one is already satisfied because of these two rows. What about this B determine D?
We can take second and the third row for that.
Second
Yeah,
and
because
third,
B is 5.
Third, yeah, 5. Yeah, exactly.
yes. So we want same alpha value, na. So same alpha value. What is D here?
7 and 3. Yeah.
7 and 3, right? Now we can swap this one. Instead of 7, it will be 3. Instead of 3, it will be 7.
7.
Now we got two new rows. So I'm writing it down here. 0, 5 will be like that. 0, 5, 6, 3, 8, right? 0, 5, 2, 7, 4, right? So these two rows must be present. Is it fine, or do we need to add few more rows? Yes, anyone?
So one doubt over here, when you're checking for this B uh, B multi def, what is it, determine D, right? So
Hmm.
A should also be constant there because you are not changing value for A, no?
Yeah, so A will be 0, 0, 0 only, na. All values will be 0
And like
only.
if we have like 0 1, so then for that we cannot take these two rows, no? If for one we have 0 in A and for another we have 1, so can we take these two rows then also?
Sorry, I'm not getting it.
Sir, can we take first and fourth row also? Because
Yes.
B is in there also.
So in this case, in the second case, we have to apply 2 times for every unique beta value. Sorry, every unique alpha value, we have to do that. For entire relation R, in order to satisfy both the MVD, there will be 8 rows. Okay, here we got 6 rows. In the option, you can see this one, but there may be few other options as well, right? In that case, what we need to do? So we have done with the 5 5. What about this 1 1? If I swap this thing, let's say this one, right? So this B determine D. Now I can swap this 7 with 3. Instead of 3, it will be 7. Instead of 7, it will be 3. Now here also I'm getting two new rows. Those rows will be what? 0, 1, 2, 7, 4. And then we have 0, 1, 6, 3, 8. So these are the total 8 rows in the relation R such that both the MVDs are applicable. Okay. Now you can check any condition, everything will satisfy. So in the option we just mentioned these two rows, but we can give any one of these 6 new rows what we got. Okay. Okay. Any doubt what we have done here? Anyone?
For the first set, only the two rows will be swapped. Oh, so we'll have only two more rows. But for the second set, multi-valued, you will have four more, right?
For the first, yeah,
Right.
because
For the A to B, we will
uh,
have two rows only extra. But
yes,
when you go for B to D, we'll have four more rows, right? Because
yes,
the
four
unique
more.
value of
Yes, correct. 4 more rows extra, right? But entire total will be 8 rows. But why we go for A determine B first? Why not this one? Why we went for the first one?
Because there's no common alpha in B.
Yes. Yeah. So we need
But
to
how
take
will we get 8 rows, sir, in the second one?
first initially these two rows will be there. After applying this one, we got these two rows.
4
Now after
total.
4 total. Now for B, multi-determine D. By using this MVD, for every unique alpha values, we have 1 and 5. So for that, we'll get two
Okay.
rows like this. Okay. So
Yes,
8
yes.
rows will be there in total. Okay. So this is how we can check for MVD, or we can apply the concept of MVD. If this thing is present, if those two rows are already present. For example, I am just giving this particular table to you, and I am giving four options. Which of the following is are correct? A multi-determine B, B multi-determine C, like that. Now what you need to do, first thing is that there must be two rows having same alpha value. So if you look at the condition for MVD, there is one line. So two rows having same alpha value, then this condition must be satisfied, right? If you look at the slides, so two rows, that is T1 alpha, must be equals to T2 alpha. Then only we are going to check for those conditions. That is what same thing here, right? If two rows are having same alpha value, then only we are going to check for MVD. Only one row is there with the alpha value, then there is no need to check for MVD in that case. Okay. So two rows having same alpha value, then only you need to swap the beta value. Okay, that is what the concept here. So here you can see for this particular case, if you just want to check, take any two rows such that's different beta value. So for this one, we can check, swap the two rows. Anyway, we are going to get these two rows, right? Like that.
I have a question.
Yes.
We added rows to make it MVD.
Yes. Yeah.
Now, this added set, is it now 3, 4 enough?
No, not in 4 enough.
So the MVD is more to do with the data in the table, not
Yes.
not the structure.
Not the structure, right?
Okay, how do we convert it to 4 of?
Yeah. Suppose we have this 5 attributes and we have this 8 rows inside the table, but MVD exists, right? Both MVD exist here, right?
Correct.
Now we need to decompose this particular table, right?
Okay.
So for decomposition part, you can see this here. A, B is there. B determine D is there, right?
Yeah.
Now we need to decompose based on these two thing like that. So here what we can find out, A, B we can make one relation.
Separate.
B, D we can make one relation here.
Okay.
Uh, Here we don't have any functional dependencies. That is not a correct thing here. So if we have any functional dependency, then accordingly we can add that attribute here as well.
That will come separately another table.
Yeah.
Okay.
So it depends on that also. In week 6 we have discussed that,
Yeah.
because in practice assignment we have one question. Two MVDs are present, two FDs are present. In that we have applied for 4NF. Okay. Please.
Will there be any questions or checking on the 4NF?
Yeah.
Decomposition?
Yes, you can expect, right?
Okay.
But always remember, any relation having just two attributes, no need to check. It is already in 4NF, BCNF, 3NF, everything.
That's
right?
a trivial case. That's a trivial case.
Yeah. And also, if you see this AB, so what I said, at least 3 attributes are required.
Yeah.
Now let's say, for example, AB we know, MVD. But if I add C, so what I said, 2 must be independent. If you're checking for A multi-determine B, then B and C must be independent. Then only MVD will exist. What I mean by independent, B determine C or C determine B, both not exist, right? Then only we can say independent, right?
Yeah. That's okay.
Yeah. If any B determines C is present in this one, now if I make this particular relation, even though it's having at least 3 attributes, still it will be in 4NF if we look at that, because anyway A determines C will be there. There is no independent attribute in this particular case. Okay.
They can be taken as a single entity.
Yeah.
If it is dependent, right?
Yeah. If it is dependent, then if it is dependent, single entity. Independent means what you can see here.
Independent. Then there will be
1, 2, 1, 6 determining, right? Not the dependencies there. Yeah. Okay. So if you see this 4NF, we don't much focus during normalization, because this will keep getting generated every row, right? For here, we just added for 0. What if I add one more row here with 1? In that case, MVD will not be applicable, because for 0 it is getting satisfied, but for 1 it will not get satisfied because only one row is there, right? So concept of MVD is little difficult if you go in depth, but as of now, just understand these two concepts: how we swap the values, how we check the values.
This is good. Your week 6 was good. That's okay.
Yeah.
I have one more small doubt. If
Yes.
it's a BCNF schema, if I divide it into 2,
Uh,
Can
then
it be in N3?
sorry, M3.
Yeah, 3NF, 3NF, sorry.
Yeah. So if you decompose the BCNF again,
Yeah.
so yeah,
Because we need somebody has done it, so will it be in 3NF or not?
we need to check if it is a lossless decomposition, then it will be always in BCNF. But lossy decomposition doesn't make any sense. We can have any possibilities there. But yeah, it will be in BCNF because every FD is a left hand side is a key in BCNF, right? Even if we decompose like that, here also every FD will be the left hand side key only, right?
My doubt was that after decomposition,
Huh?
the subset of the FDs
Huh?
do not define. I
Huh?
mean, I was confused about how do I identify whether it is a super key or not.
Okay.
So I posted a question in the discourse. Maybe later on you can respond to that.
Discourse. Okay, I will check that.
Later. That's okay. Thank you.
Because yeah, this may happen. We need to check for the.
I came across this somewhere in the
Uh,
PYQ somewhere. I was confused, so I asked you. That's okay.
I will check that. Okay. Yeah. Sure. Okay. So this is regarding the 4NF we have discussed. So this is about week 5 and week 6 we have covered today. Week 7, just go through the slides because anyway we are focusing week 7 in OPE exam. So quiz 2, just go through the slides. That will be good enough. For week 8, we have few important topic. BS tree. Then we have this magnetic disk, and then we have this one. What we have MRU LRU, right? So simple one, binary search tree. I hope everyone knows how this binary search tree works. So you can see this particular question, right? Suppose I have this sequence like this. Let's say, for example, 6, 8, 10. Anyway, we'll discuss that thing in detail in Saturday session, but we'll quickly discuss this binary search tree. 4, 2, let's say 5, like that. Now, how we are going to insert? Let's say we have an empty binary search tree. Now we are going to insert this element. So first we are going to insert the 6 that will be there. Now what happens here? Whichever the element we are going to insert, we are going to compare with this node. Now if it is greater than this particular element, we are going to add on the right side. If it is less than this element, we are going to add on the left side. Okay, that is how this binary search tree is constructed. For example, 8. 8 is greater than 6. Yes. So that will be on the right side. Similarly, 10. Again compare with 6. Again compare with 8. Again greater than 8. So that will be on the right side. Right. Again, what about 4? Less than 6 on the left side. 2 less than 6 but less than 4 as well. That will be on this particular side. What about 5? Less than 6 but greater than 4 here. Then it will be on the right side like this. What about 9? Greater than 6, greater than 8. So it will be on right side. But what about 10? It is less than 10. So that will be on this side, right? That's how this particular tree is constructed. So you should be able to construct the binary search tree if given sequence. What is height? What is leaf node, non-leaf node? What is subtree of this thing? What are the levels? Everything you should know about this binary search tree. Okay. So, but first thing,
Sir,
binary
can I
search.
ask something? Here you took you added 9 to the left of the 10. Why can't we take it on the right of 2 or the right of 5?
No, first we are going to compare with the root node here, right? So 9 is greater than 6, right? So it will go
okay.
on the right side. Again compare this with this one. So again 9 is greater than 8, again go to right side. Compare with this one. 9 is less than 10, so go to left side. So that will be on the
Okay.
left side.
We start from the parent or the root node, then keep on
Yeah.
comparing. Yeah.
Comparison. Yeah.
Got it.
So this will be a level 0, this will be a level 1, this will be a level 2, this will be a level 3. So what is the height here? Height of the tree?
3, sir.
Yeah, that's it, right? So in this way, you can expect a few questions and do solve this question, simple one. Multiple sequences are possible for the same tree. Remember that MSQ is there, so multiple things are also possible. In this question, only one option is correct, but multiple can be also possible. Okay. Okay, so that's it. We'll discuss in next session about week 8. week 7 just go through slide, that will be good enough. MRU, LRU I already discussed in the previous week 6 session. You can go through that. Similar, same example is there, but just the numbers are different. Okay, then we have this magnetic disk. Remember the formulas, watch the tutorial, that will be good enough. Okay, yeah.
Are
Any
there
doubt?
going to be, are there going to be something to do with the syntax of the
Syntax of?
APIs, SQL APIs, Python and all?
No, no, no. Simple, just go to the slides. Like what we said, which function is used for which purpose, right?
Yeah,
Like this question.
that's correct.
Yeah. So all the concept regarding Python database connectivity, we are going to check in the OPE exam, right? Yeah. Okay, that's it from my side. All the best for.
Thank you very much.
Thank you.
Sir, what you discussed after that multivariable dependency,
Multi-value dependency.
yeah,
After that,
week 7.
no, not big 7. Just go to the slide. I just discuss this
Oh,
binary search
okay.
tree, one simple concept.
Yeah, that is okay.
Yeah,
Okay.
yeah.
Thank you, sir.
Okay. Thank you, everyone. Bye bye. I have one more session now. Yeah.
Yes.
So you'll be sharing this PDF, right?
Yes, yes. I will be sharing. This is a solution PDF for mock test 2 only. So I will be uploading this one. Not the written one, but along with the solution. Yeah.
Okay, sir. Thank you.
Okay. Thank you. Bye bye.